Okay, so let's talk about refraction. Now, refraction just means bending, and we're going to specifically look at this glass block with a beam of light coming from a ray box. Now, you might have done this practical at school, so hopefully you remember it, but let's talk through it. So I've got this beam of light shining from a ray box, and a ray box is just literally a little black box, and it's got a light bulb in it, and you've got a slit so that only one beam of light passes out. Now this ray here is called the incident ray, and it's the one coming from the ray box to the glass block. Now at the moment that ray is travelling through a gas, it's travelling through air. So it's travelling really quickly because gas particles are further apart, so it can pass through really quick. But here we've got a glass block which is a solid. Now if you remember, solid particles are much closer together, therefore the ray slows down, and because it slows down, that's why you get that bending, because we've gone from a less dense medium to a more dense medium, and medium is just another word for material. So what happens at this boundary then between the air and the glass block? We have to draw in something called the normal. Now the normal is just a dotted line, it's 90 degrees to the glass block. So what happens is the ray will bend towards the normal like this. So can you see, if I didn't bend that ray, it would have continued going like this. But that's not correct. It bends towards the normal as it goes into the glass block. So again, we have to draw a normal in at the other end. And what I always try to do is, now that we're going back out into the air, I try to draw this ray and that ray very, very similar. So I don't have a ruler right now, but make sure you have one for the exam. So slant your ruler and have a look at that sort of level and distance, and try and copy it over here so that they look the same. It's just so, you know, the examiner can see that this ray and that ray are at the same angle, and that you understand that they're both in air and that you've bent this one between those two. So in terms of angles, let's just have a look now then. So this angle here between the incident ray and the normal is known as the angle of incidence. Okay, and this one here, where the ray was bending towards the normal, is called the angle of refraction. So just so you can see here, as we're going back out into the air from the glass block, this one bends, this ray bends away from the normal. And like we said, this one bends towards the normal. Right, let's talk about the EM spectrum, so electromagnetic spectrum. You do need to know the order of the electromagnetic spectrum, because often there's like a fill in the blanks question. So electromagnetic spectrum. So let's start with, right, radio waves. I'm just going to write it in order in shorthand because I don't really have that much space. So radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma, or gamma rays. So radio waves have the lowest frequency. Now, lowest frequency, if you remember, means you don't have that many peaks per second, whereas gamma is high frequency, it's the highest frequency. So frequency increases as you go from radio waves to gamma rays. So if this one has the lowest frequency, it means it's got the longest wavelength. So lowest frequency, longest wavelength, and you can see here wavelength is short, so this one here is the shortest wavelength. So wavelength decreases. So all EM spectrum waves are transverse waves, so really important that you remember that. Don't ever say that they're longitudinal, because they're not. They're transverse waves, and transverse waves were those ones. So let's talk about these individually. So starting with radio waves. So radio waves are used for communication. Now you need to be able to state one use for each of these waves, so it's best to remember just one for each really. So radio waves are used for communication. Now communication is in terms of let's say radio, the radio station sending signals and it reaching your home. That is effectively communication. So radio waves work by, here's the earth, here is a band above the earth called the ionosphere. Now short wave signals let's say they want to get from this point to this point. Shortwave radio wave signals reflect off the ionosphere and bounce around the earth like this to get to the point that they need to. So they're not long enough to get all the way around the earth. They can't bend around the earth, so what they do is they reflect off the earth. Maybe, sorry, mine's not, I should have done that a bit neater. Maybe something like that, where they're reflecting back and forth off the ionosphere to get from one point to another. Whereas long wave signals can bend around the earth. So from this point, let's say they want to get here, they can bend around the earth, so they don't need to reflect off the ionosphere. Now an example of long wave signals is radio. So when you're listening to the radio, those waves can bend around the earth. Whereas shortwave signals, we're talking about something like Bluetooth. Right, so microwaves then. So microwaves are used for, microwaves is also communication, but it involves satellites. So microwaves, again, communication or heating food. So here's my earth. Above the earth we have a watery atmosphere. So this isn't involving the ionosphere now, it's involving the watery atmosphere. And here's my satellite in space. Now it could be a TV satellite, it could be your phone company satellite, but the message, the microwaves are sent, they can pass through this watery atmosphere to the satellite, and then so they reach the satellite and a signal is sent back through the watery atmosphere to somewhere else on Earth, probably, you know, to your home, wherever you're watching TV. So sometimes there is a delay, and you might have seen this, you know, when you're watching TV and it cuts out, the program cuts out slightly, or there's a bit of a time delay, and that's because of the time it takes to get to the satellite and then come back down. There is a short delay. But in terms of heating food then, what happens is, let's say that's my microwave is in the appliance. There's my food. So the microwaves penetrate the food just a couple of centimetres. They then pass that energy to the water in food. So what they do is the microwaves penetrate about a few centimetres into the food before being absorbed and transferring the energy to those water molecules in the food. Okay? This causes the water to heat up. The water molecules then transfer the energy to the rest of the molecules in the food. So that's how microwaves work, and that's how your food gets cooked really, really quickly. So it's microwaves, travel a few centimetres into the food, they transfer their heat to water in the food, and then the water transfers it to the rest of the food molecules. Right, next one then is infrared. Now infrared can be used for thermal imaging or thermal cameras, and also with TV remote controls. So TV remotes, or like a DVD player with the remote between the DVD player and you know, you press on, there's a bit of a red light that flashes. So infrared. So thermal cameras, if you don't know, are just those you know, those almost night vision cameras. You can see things in the dark because of the heat energy that's being given off by something. So let's say here's a person and it's dark and we're using a thermal camera. So infrared is basically given off by all objects, so including humans, animals, etc. So the more infrared that's given out, the hotter the object. So for instance, our core, the centre of our body, will give off the most heat. You know, it's the warmest, our core temperature is the hottest, therefore more infrared is given off from that area. So on the image, that area will probably be the really, really red image, as opposed to somewhere else like our fingers and toes, which don't give off as much heat energy, and therefore it will look a different colour in the thermal camera. So what happens is the camera detects the infrared radiation and turns it into an electrical signal. And this electrical signal will be displayed on a screen where you can see, you know, here's more red and here's orange and etc. So it's just a way of using temperature to see an image. Okay, visible light. So visible light is used, just normal cameras, or you could say fibre optic cables, which are just really, really thin cables allowing the visible light to bend through. So visible light is all the colours of the rainbow, so it's everything we can see. So this is a fibre optic cable, I've just zoomed into it. On the end, a visible light is seen. Now I'm just going to show you how the visible light bends through the fibre optic cable. Now this is a typical exam style question where they ask you to draw how the visible light gets from one end to the other. Now what you have to do is you show it reflecting off the cable like this, but it's really important that you show that it's bending, that it's reflecting through the tube at the same kind of angle. So don't do this, don't start, you know, doing this. That's not how it goes through the tube. It will go really nice and neatly at the same kind of angle. Now, so we just call this refraction, which again means bending. Okay, so that's visible light. Ultraviolet. So ultraviolet gives you a suntan. Now ultraviolet is used in sunbeds or tanning. The sun gives off UV radiation as well. So what happens is ultraviolet radiation is absorbed and then visible light is emitted. That's how fluorescent objects